Okay, so we're given a normal distribution question here, and we know that x is distributed normally with a mean of 25 and a standard deviation of sigma. So let's start by just drawing ourselves a little helpful graph, and there's my 25, and we know my 24.63 is down here, and I know that this area here to the left of 24.63 is going to be 0.15. So we're going to formalize that, and we're going to write that then as the probability that x is less than 24.63 equals 0.15. Now, we can't do this directly on my calculator because I don't know what sigma is, so I'm going to need to standardize, and so I'm going to put this into z form. Probably the z is less than 24.63 minus 25 over sigma equals 0.15. Now I'm going to need to standardize that 0.15, so I'm going to use my inverse normal function. So let's have a look at what we do on the calculator. I'm going to do menu 7 for my distributions. I know that the probability is 0.15, so I've got an area of 0.15. It's my standard normal, so sigma is 1, mu is 0, which is what the calculator defaults to, and it gives me minus 1.036. I'm going to just store that in my memory. So I can say now that's minus 1.036, and 24.63 minus 25 is 0.37 over sigma. Rearranging that, I've got minus 0.37 divided by my answer. Oh, let's go into my normal screen. Minus 0.37 divided by my answer gives me sigma of 0.357. So I can just say here, sigma equals 0.357. Well, let's go back to the diagram that we had drawn before. I'm just going to save my 0.357, my sigma there, just to make sure I've got an accurate drawing. Let's just be clear as to what's going on. So I now know that my mean is 25. I've got 24.63 is down here, and I know that this area over here is 0.15. The area between 24.63 and k is 0.45. So k must be to the right of 25. There's my k. And I know that this area is 0.45. Well, we need to recognise then that the total area to the left of k is 0.45 plus 0.15, which is 0.6. So I can say the probability that x is less than k is 0.6, and I can use my inverse normal function again. So going back to my distributions, menu 7, inverse normal, my area is now 0.6, my standard deviation is what I'd stored in A, and my mean is 25. I should get an answer greater than 25 here, and it gives me 25.09. Okay, so going on to part B, we need to be careful here because we're no longer looking at the amount of perfume in each perfume bottle. We're looking at the number of perfume bottles which fulfill this criteria, which looks as though it would follow a binomial distribution. And it tells us that to use a normal approximation, let's firstly write out what the binomial distribution would be. So x would be distributed binomially, n, which is 200, p, well, the probability being between those two values is 0.45. Now, using our formula booklet, I can just give you the page of the formula booklet here, it's on page 8. We've got our mean and our variance for our normal approximation. The mean is going to be NP, the variance is going to be NP1 minus P. Remember, we're going to need to square root that to find the standard deviation. So, that can be approximated by y, which is going to be distributed normally NP 200 times 0.45, and with a variance 200 times 0.45 times 0.55. And we're just going to remind ourselves of that variance by putting square root and squared on it, so that we can remember that we're looking at the square root of that when we want the standard deviation. That means that we can say that y is normally distributed 90, 200 times 0.45 times 0.55, square root of 49.5 squared. So, the probability that fewer than half of these bottles contain, so that's the probability that x is less than or equal to 99. Now, we're going to need to change that slightly by doing something called a continuity correction. So that's going to be equal to the probability that y is less than 99.5. Now, just very quickly, the reason why it's 99 rather than 99.5, if you look at your binomial distribution, let's say that's 98, 99, 98, 99, 100. If we're looking at less than 99, we're approximating that by a normal distribution. What we're going to need to do is, rather than 99, we're going to need to say less than 99.5, because those bars come up to the midpoint. So we're always going to go to those halfway points when we're doing our continuity correction. So the probability that y is less than 99.5, I can do that straight away on my graphics calculator. So I'm going to say here, let's see the full screen. We're going back to my menu, distributions. I'm trying to find a probability, so it's going to be normal CD. My lower bound, well, I don't have a lower bound, so I'm going to put minus 9999999. Upper bound is 99.5. Sigma is the square root of 49.5. And the mean is 90. And it should give me a probability of 0.912. The last question here asks us to do a hypothesis test from a sample mean. We need to know, and this isn't in the formula booklet, that if x is distributed with mean comma sigma, x bar is distributed normally with the same mean, but the standard deviation becomes sigma over root n. Okay, so you're dividing that standard deviation by the square root of n. Let's just set out our hypotheses. H naught is that mu is, is that H naught is that the mean equals 25. H1, her alternative hypothesis, is that mu is less than 25. There's been a reduction. So here we're saying that there's my normal distribution, my mean of 25. She's ended up getting 24.94. I'm trying to find the probability that that happens under the null hypothesis. So that's the probability that I'm trying to find. If that's less than the significance level, then I would reject the null hypothesis. Well, let's just check. Under the null hypothesis, x bar would be distributed normally 25, 0.16 over root 20 all squared. I can do that straight away in my calculator. So I'm going to go into my menu, option 7. I'm trying to find a probability, so it's normal CD. Lower bound, I'm going to keep as minus 9,999, or whatever I had before. My upper bound is going to be 24.94. My standard deviation is 0.16 over root 20. And my mean is 25. And I'm trying to work out the probability. The probability there is 0.0468. .68% is less than 5%. Implies I reject the null hypothesis. And Hannah is correct.